Alright, today we're talking about 3.5, which is velocities. We're going to start today with a question. So if the specifications for a Ferris wheel indicate that one trip around the wheel took 20 minutes, how fast was the rider traveling around the wheel? Now there are a couple ways of answering this. One of them, the standard ways to answer it is, how far around the outside of the circle are we going and how fast does it take to do that? And that's called linear velocity. But there are multiple ways to do it. Like we said, the main way, the most intuitive way, is to say linear velocity. How fast around the outside of the wheel are we going? We pick a distance in arc length around the wheel and see how much time does that take. The units of linear velocity would be miles per hour, feet per second, meters per second, that sort of a thing. But another way to think about it is what we call angular velocity. Now, angular velocity is given by the amount of central angle through which the rider goes over a given time. So if we redraw our Ferris wheel and draw a central angle, any central angle really, theta, we have this given theta. Instead of going around the outside of the circle, how much do we move through this central angle over a given amount of time? And the units for that would be more like radians per second or radians per minute, or perhaps degrees per minute, degrees per hour. It could be any of those. So let's try this out, right? In the original statement, the wheel goes one full rotation in 20 minutes. So we got to find the angular velocity in radians per minute. So we want to figure out the angular velocity in radians per minute. Well, right now I know that this wheel goes one full rotation in 20 minutes. Well, if we look at our problem, we want the final answer in radians per minute. Note, I already have minutes, but I have a rotation instead of radians, so I got to switch rotations to radian. Well, remember, I know that one rotation, we're going to say 1 ROT, is one time around the circle, which is 2 pi radians. So when this problem says it goes one full rotation in 20 minutes, we can also think of it as going 2 pi radians in 1 minute. So we know then that our angular velocity is 2 pi radians per 20 minute, or simplifying down, pi over 10 radians per minute. However, what if they ask for it in radians per second? Right, we already know it's 2 pi radians, but we have to change 20 minutes to seconds now. Well, I know that per minute there are 60 seconds. So I'm going to multiply this by 60 seconds to get my seconds now. The 60 seconds per 1 minute. My minutes cancel. 60 times 20 is 1,200 seconds. So now I take 2 pi radians divided by 1,200 seconds. Simplifying that down, I get pi over 600 radians per second. So depending on what the question is asking from us, we might have to change our information in order to fit the units or the way they want us to answer this question. So let's do some practice here. Oh, sorry, no, beforehand, we're going to define this now. So angular velocity, what we just talked about, right? We took the angle theta and divided it by however much time we were dealing with, right? We had 2 pi radians per 20 minutes, or however many seconds, or however much time we're dealing with. And we call the angular velocity omega. That's not a W, it's an omega. So we always say omega is equal to theta divided by time. And theta does not have to be necessarily in radians. It can be in degrees or revolutions. And the time unit can also be anything, right? Hours, minutes, seconds. The only thing we have to be careful about is knowing whatever the question is asking us to answer it in for units, we have to change our information, our theta or our time, in order to fit that. So now let's take a look at an example. So a point on a circle rotates through 3 pi over 4 radians in 3 seconds, right? Let's draw a picture. 3 pi over 4. So let's say our point is right here. 3 pi over 4 is not quite 1 full pi. but it's about right here. Remember, if we were to draw our unit circle out, our reference angle is 45, or pi over 4. So this is 3 pi over 4. So that's our theta. Our theta is 3 pi over 4 radians. Our time here is 3 seconds. Let's look at the units they want the answer in. They want it in radians per second. Well, I have both of those, so let's just plug it into our formula. Omega is equal to 3 pi over 4 radians divided by 3 seconds. My 3's cancel, and I'm left with pi over 4 radians per second. Box the answer, and that's all there is to it. Another one, a point moves through 60 rotations per minute. Give this angular velocity in radians per minute. Right, my answer is asking for radians per minute, but I have 60 rotations per minute. So I need to change this rotations per minute to radians per minute. Well, remember that one rotation is equal to 2 pi radians. So if I know that one rotation is 2 pi radians, if I want the 60 rotations per minute in radians, I just need to multiply this by 2 pi radians per one rotation, because I want to get rid of the rotations. So my rotations cancel. My units will be left with radians per minute. So I get that my final omega is 120 pi radians per minute. All right, let's switch gears a little bit and talk about linear velocity. Now remember, the linear velocity is a point on the circle and how far around that circle it goes. So if I have this point on the circle, the linear velocity is the velocity it takes going around the circle. So the distance it travels divided by the time. Remember, we're in a circle though, so we're dealing with the arc length of the circle. That's where we get this s from. So we get s over t as one of our definitions. Well, remember, we defined arc length as r times theta. So that's how we get from this second definition as linear velocities r theta over t. We just substitute r theta in for s, our original definition for arc length. But remember, theta divided by t, we just define that as omega, angular velocity. So we can also write linear velocity as r times omega. So we have three different definitions that we can use. And in order to figure out which definition we're going to use, we have to look at the information that the problem gives us. So let's do a few examples to illustrate this. A circular saw blade with radius 5 inches rotates at 600 rotations per minute. So we need to first find the linear velocity of the point on the outer edge of the blade in inches per minute. Inches per minute. So we're going to need to make sure we have those units. Okay, I have a radius of 5 inches. So r is 5 inches. I also know my omega is 600 rotations per minute. So one thing to kind of get in the habit of is that we're going to want to change omega to radians per minute, because radians are a unitless degree. We don't want this pesky rotations unit floating around in there. So I'm going to change 600 rotations per minute to radians per minute. In order to do that, remember, we need to multiply by 2 pi radians, because 2 pi radians are in one rotation. My rotations cancel, and I'm left with 1200 pi radians per minute. So we're going to use that instead of 600 rotations per minute. So going back to the previous slide, what formula do we want to use? Well, I have a radius and an omega. A radius and an omega. So I'm just going to plug both of those into my linear velocity equation. So my r is 5 inches multiplied by my omega. Remember, we changed omega to 1200 pi radians per minute. Plugging that into my calculator, it's going to come out with an answer of 6,000 pi inches per minute. To give you kind of an idea of what that actually is, it's about 18,849.6 inches per minute. Now, then it says to convert it to miles per hour. Right, I'm in inches per minute, so I need to change everything over to miles per hour. And this is how we're going to do it. Write down your original value that you have, 18,849.6 inches per minute. Now I want to get rid of minutes and turn it to hour. Well, I know that per 1 hour I have 60 minutes. So my minutes are gone. Now I have inches, and I want to convert that to miles. Now I know a conversion factor of per 1 mile, there are 63,360 inches. My inches are gone. We're going to plug all of this into my calculator to get 17.85 miles per hour. Let's do another example. A bicycle wheel with radius 13 centimeters turns at 3 radians per second. Find the distance traveled by a point on the tire in 5 minutes. Okay. So this is your typical linear velocity equation. However, we have one more step to do at the very end, and that's to find the actual distance it travels. So let's first find the linear velocity. Notice I have a radius, and I have an omega. I have my angular velocity. So we're going to plug that in to find v. 13 centimeters times 3 radians per second, giving me an answer of 39 centimeters per second. Now, if I'm driving a car, and I want to know, and I know my speed, say I'm going 25 miles an hour, and I want to know how far I can go in 5 minutes, what I do is I take my speed and I multiply it by the amount of time that I'm driving to find the distance I've traveled. We're going to do the same thing here. I know my linear velocity, I know my speed, and I know the time that I'm traveling. So what I'm going to do is I'm going to find d, I'm going to take my linear velocity, 39 centimeters per second, and I'm going to multiply it by the time I go, the time I'm traveling. However, notice the time is in minutes. And right now, my velocity is in seconds. So I need to change my time, my 5 minutes, into seconds in order to multiply things out here. Your units always have to match. So I have 5 minutes, and I know that per 1 minute, there are 60 seconds. My minutes cancel. I put that upside down. I wanted to do that a different way. My apologies. Minutes should go on the bottom here. There are 60 seconds per minute, which gives me that there are 300 seconds here. Apologies on that. Bit of a mind blank on that one. So I'm going to multiply this linear velocity by 300 seconds, which gives me 11,700 centimeters. Notice my seconds cancel, leaving me with only centimeters. So the distance I travel is 11,700 centimeters. Now, kind of a fun applied problem here is if I know that one rotation on the Earth takes 24 hours, and the radius of the Earth is 4,000 miles. Let's find the linear velocity of a person standing on the equator in feet per second. Remember, feet per second. So I have to change both of my measurements here to feet per second instead of miles per hour. So let's start off with changing miles to feet. We're going to need lots of space here, so I'm going to start up on top. I have 4,000 miles. And I want to change that to feet. Well, I know that 1 mile is the same as 5,280 feet. Plugging that into my calculator, I get 21,120,000 feet. So that's the radius of the Earth in feet. Now I also need to change my hours into seconds. So I have 24 hours. And I know that per 1 hour, there are 3,600 seconds. 60 times 60 to get minutes and then to seconds. My hours cancel, and I'm left with 86,400 seconds, which is the amount of seconds in one day, 24 hours. Well, okay. So I now have the radius of the Earth, and I also have one rotation. In order to find out the linear velocity, though, I need a radius and I need an omega, an angular velocity, and I don't quite have that yet. But I do know that the Earth, that one rotation, 1 RPM, one rotation of the Earth takes 24 hours, or 86,400 seconds. So I can find out what my angular velocity is. I know that my omega is 1 rotation, 2 pi radians, divided by the amount of time it takes to go all the way around, 86,400 seconds. Simplifying that down, it gives me pi divided by 43,200 seconds, radians on top. So I have an angular velocity of pi divided by 42,200 seconds. Now in order to find linear velocity v, remember our formula we were given, r times omega. I have r. R is 21,120,000 feet. Times my omega, which is pi divided by 43,200 radians per second. My radians are a unitless degree. Plugging all this into my calculator, I get that v is 1,535.89 feet per second. So while it might seem like you're standing still when you're not moving at all on the Earth, you're actually traveling at about 1,500 feet per second. All right, go ahead and write your summary and any questions you may have, and then take a look at the assignment on page 159 for tomorrow.